Yeah, welcome to this class, everyone. I'm your physics instructor. Today our topic is projectile motion. For that class we've talked about motion under gravity, but now I want to talk about projectile, which is also part of motion under gravity. But we're going to have different views on vertical projectile and horizontal projectile. Now, first of all, let's understand what projectile is all about. Projectile is just a name given to any motion of a body that tends to pass through a parabolic path. A parabolic path meaning if I decide to hit a ball and the ball from where it was kicked and it moved like this, maybe, and this is the ground level. This part where it passes through, this part is parabolic. So you say it's a parabolic path. Now, whenever the motion of a body turns or passes through a parabolic path, we say that that body is a projectile motion. But this projectile motion can be horizontal. For example, if I have a projectile that looks like this, maybe I kick a body with an initial velocity u, a meter per second, and the body tends to move in such a way that it lands, and this is the vertical component, this is the horizontal component. This kind of projectile, it moves from this place where it was projected, it moves down until it finally lands. This kind of projectile, I'll call it a horizontal projection. Horizontal projection. But there are some time, horizontal projection, sometimes you have projectiles that are different. Maybe this is a building standing, and you decide to shoot a body from here with an initial velocity u, a meter per second, and the body now trek until it hits the ground like this. This is the ground level, this is where it hits the ground. This kind of projectile is called vertical, but most times we call it tragedy of a projectile. Now, but the tragedy of this projectile can be calculated, but that's as we continue with our class. Now, I'll start with projectile of this form, but before then, let's see some of the uses of projectile. What can projectile do for us? Examples of projectile. Most times I'm a kind of sport person. I love this game they call javelin. When you watch the javelin game, you see when they throw the javelin, it tends to pass through a parabolic path. Somebody hitting the javelin, it moves, and it finally hits the ground. It's in a parabolic path. Another example is you kick a ball, the ball moves. It's a parabolic path. Another example, those people into shot puts, the ones into height swimming, maybe taking it from a certain height, jumping down, it's projectile. Because when they jump, they passes through a parabolic path, probably, which tends to become a tragedy. Now, those are some of the examples of projectile. Other examples of uses of projectile. In that case, you have uses of projectile basically for sports. By the time you shoot a javelin, you hit a ball, you calculate the projectile. When the ball finally hits the ground, that's one of the uses in sports. The second use of projectile is in warfare. Warfare. So, now, so we have uses of projectile. Number one, in sports. Number 2, in warfare. Now, for warfare, I've explained sports, and warfare is a different thing entirely. For example, you have a helicopter, or probably a jet bomber. You want to bomb a certain target. Before you can bomb that target, you need to know the projectile at which your missile will move from your bomber to hit that particular target. So the plane or the jet bomber has a signal that can measure projectile of locations. So by the time the body is somewhere here, for example, that's the bomber, this is the point where you want to hit. You just see the thing just move, trek and hit. So this part at which it passes is a parabolic part, and that's the ground level. So it hits, it hits, it hits. They tell you that that is your target. So for those of people who are in Air Force, they'll tell you more about projectile. They tell you want to hit a target, you need to measure the projectile of that target from your bomber. So basically, projectile is used in warfare. So remember, projectile is used in sports and it's also applied in warfare. Now, that's that. Now, we want to start talking about projectile in terms of dew box calculation. Now, when I hit a ball from here with an initial velocity u, a meter per second, the body will trek until finally hits the ground. When you hit the ground, simple. This is the vertical component, and this is the horizontal component. Now the question out there you're asking yourself, you always hear teachers use the word component. What's the meaning of this thing called component? Components just simply mean it's the vertical direction with respect to the angle and horizontal direction with respect to the angle. And don't forget there is an angle here, theta. Vertical direction with respect to the angle, vertical direction with respect to the angle, horizontal direction with respect to the angle is called the component. Now, from here, horizontal component, vertical component. But how do I know what value is going to be here? Sometimes you've seen your teacher, you will just write something here, u cos theta, and here you will write u sine theta. I don't know that this is u cos theta, this is u sine theta. Why? I don't know that. Okay, good. I'll explain that to you. There's a very good friend of mine. His name is Lamins. Lamins. That's his name. Lamins. So most time we'll say Lamins theorem. Lamins discovered something. He said in his deductive rules. His deductive rule was simple. He said, wherever the angle is, anywhere you find the angle, it is sine. No, sorry. Anywhere you find the angle, it is cos. Where there is no angle, it is sine. Let's take it again. Lamins discovered that where there is angle, it is cos. Where there is no angle, it is sine. Look at it. If this is u, for example, because there is angle here, automatically this direction becomes u cos theta, and here becomes u sine theta. Because there is no angle, it has to be sine. Because there is angle, it will be cos. But what about if you have a situation where is the reverse? Here is 48 degree, and here is, this is 10 Newton. This direction, there is no angle here. So because there is no angle here, here is going to become 10 sine 48 degree. Because there is no angle, it's sine. Here become 10 cos 48 degree. Because here there is angle. So always remember, Lamins, in his resolution principle, that wherever there is angle, cos. No angle, sine. I'll take it again. Where there is angle, cos. No angle, sine. Beautiful. So from here, that's the reason. Because there's angle here, cos. There's no angle here, sine. Now are the two things again. From this place where this body was hit to where it finally landed on the ground, you can call that place range. It's called the range. Not the rover, but the range. It's the range, but not the rover. So, from here down to this place, that's the range. That's the distance from where the body was shot to the distance, or the horizontal time, to where the body finally hits the ground. Is called the range. Now, there is another thing we can calculate. From this place where you get to the highest point, it got to that point, that was the highest level you get to. So at that highest level, we call that place the maximum height. Capital letter H, maximum height. You know, when it moves from this point, it gets to this maximum before it starts falling back to the ground. That is the maximum height it can reach. Now, this highest distance it can reach on the vertical axis is maximum height. On this side, it's horizontal. So remember that, please. Now, from here, what are the things we can calculate from the whole of this setting? Let's see the things we can calculate. The things we can calculate is simple. The first thing we can calculate is the time to reach maximum height. The first one is the time to reach maximum height. Now, time to reach maximum height means time to move from this position until it gets to this position. That is the time to reach maximum height. But that time has a value. It is given as small letter t and is equals to u sine theta over g. Take note of that. Let's not go into deductions. That's okay. Now, the second one is 2. Another thing we can deduce from the whole of this setting is time of flight. Time of flight. That time of flight has a value. It is t and is equals to 2u sine theta over g. Now you can see that the time of flight is 2 times time to reach maximum height. So that is, sorry, that's capital letter T. That is, capital letter T is 2t. So when you use 2 to multiply this, you get this. So time to move from here to here is time to reach maximum height. But time from here down to the final point is time of flight. Or sometimes you call it total time of flight. But it is time of flight. Time of flight from here down to this point. Beautiful. Now, let's take the third thing we can calculate from here. That thing is called the maximum height. The maximum height. You see, because it's big, it's large, it's called the maximum height. Now, maximum height, you have height is equals to u squared sine squared theta over 2g. That's the value of maximum height. Now, there's another thing we can calculate, which is the fourth. That thing is called the range, which I discussed here. The distance from here to this point on the horizontal is called the range. This is the maximum height, or the height reached. Now, the range is equal to u, 2u, I'll tell you, we'll have to take the relationship between the two of them, between this and this. But first of all, you must understand that the range is UT. That's the first thing we must remember. Always remember this. Or we write it as U times T. What means by U times T is initial velocity of projection times the time of flight, which is the total time of flight. We'll come to that. Now, the range also the range, R, in terms of the angle of projection, is also equals to U squared sine 2 theta over G. Now, this is range, this is range. This is the height of the body, the time of flight, and the time to reach maximum height. Now, I can relate these two together. But before then, the range of the body can reach something they call maximum. But the range can only be maximum at certain time. Now, how can it be maximum? If you check this value, maximum values of range is attained when angle theta is equal to 45 degrees. That is, range is maximum when theta is equals to 45 degrees. So the range is maximum at 45 degrees. What does that mean? Let me give you an explanation. If, for example, you have something like this, a body move maybe 10 degrees, that was short. This is the range. Maybe the range, this is the range, x1. When you shoot it again, that is x2. Probably we shoot again, that is x3. Now, after you've reached 45, if you shoot higher than this, it will be coming back now. If you shoot again, it will now be coming back. If you shoot again, it will now be coming back. Until the final shoot you will shoot, that it will be 0, will be 90 degrees. So when you shoot, as you are shooting, 10 degrees is increasing, 30, 32, 40, 41, 43, 44. Immediately you get to 45, that is the maximum it can reach. But when you exceed 45, instead of to be moving forward, they start falling back. The range measured on the ground level will start falling back. From 45, which is the maximum, it will start coming back. If you throw the next one, it will come back. Going as high as it is until there's one that you throw that the range will be automatically 0, which becomes 90 degrees. Because if you throw it straight up, it will fall back. So what you throw up and falls back, you cannot measure the range. So it's automatically 0. Now, from here, they say theta is equals to 45. That is when range is maximum. So therefore, range maximum, which is maximum range, is equals to u squared sine 2 into 45 degrees divided by g. So this will give us, that will give us u squared sine 90 degrees. And we all know what 90 degrees is. Divided by g. So when it's 90 degrees, that's automatically equal to 1. So range is maximum at u squared over g. So always remember this one. Range is maximum at u squared over g. Good. So the next value we're going to have as far as range is concerned. We can also have maximum height. We can have maximum height as u squared over 2g. Initially, the highest height reached is u squared sine 2 square theta. So at maximum is u squared over 2g. And recalling that arrow maximum, which is range maximum, is also equals to u squared over g. Now, how do I relate these two together mathematically? I'll bring them together. Now, look at this. From here, if I take this first, this can be rewritten as h max is the same thing as 1 over 2 times u squared over g. These two values, they are the same. 1 times u is u squared, 2 times g is 2g. Now, but we remember that arrow max is u squared over g, which is this. Now, if I replace this value is equals to this. So why not just replace it with arrow max? If I put arrow max here, you have h max is equals to 1 over 2 times arrow max. So therefore, h max is equals to arrow max over 2. So please take this relationship. The relationship between maximum height and range, maximum range, is h max is equals to arrow max divided by 2. Good. Now, we've talked about this. You remember you're noting range is maximum at theta is 45 degrees. Immediately exceed 45 degrees, begin to reduce. And the lowest you can get is at 90 degrees, which is 0. Now, from there, that is arrow max is u squared over g. Now you can remember your time to reach maximum height is u sine theta divided by g. Time of flight is 2u sine g sine theta divided by g. And this is h is equals to u squared sine square theta divided by 2g. And the last is range is u times t. Always remember this is initial velocity times time of flight. And from here, what do you get? You have u squared. From here you have u squared sine 2 theta divided by g. Now, you're saying from here we've been able to draw out these values. So you take note of that. Now, we'll take a very interesting question on this. Okay? Now, we'll take a question for projectile. Now, from this question, you'll discover that a body is projected with an initial velocity of 4 meters per second. You know, you circle, you know what that value is. That value is u. Okay. At an angle of 60 degrees, that is theta, to the horizontal. Good. It said calculate A, time to reach maximum height. Let's start with the time to reach maximum height. That is solution A. Time to reach maximum height. If you remember, you have T is u sine theta over g. What's the value of g? That's 10 meters per second square. Good. Now from here we have the value of u is 4 times sine 60 degrees divided by 10. 4 times sine 60 degrees is 0.866 divided by 10. Now, if you have that as a value, what do you calculate? You have 4 divided by 10. That's 0.4 times 0.866. That gives us 0.35 seconds. That's our value. Now, B is this gone. It's a time of flight. Time of flight, surely t is equals to 2 small t, and that will give us 2 times 0.35, which is 0.70 seconds approximately. Now, question C. Question C, you have maximum height reached. The maximum height reached, h, is u squared sine square theta over 2g. So from here, you have your u to be 4 squared sine 60 degree all squared divided by 2 times 10. Now listen, sometimes when you're taking your computations, some students get this wrong. When they get here, they look at this value, sine square theta, they ask, well, what does sine square theta mean? You don't need to bother yourself. What they actually mean is the same thing as when you say x squared. So it's the same thing as sine theta squared. So it's just mathematical writing. There's nothing there. So what you just need to do is take your sine theta and put the square there. So from here you have 16 times 0.866 divided by 20. So in your value point, what do you calculate? From here, within computation, you have 0.6 meter, approximately. You put that down. Now, we'll have the last value, which is range. As D, range is u squared sine 2 theta over g. That will give us 4 squared sine 2 into bracket 60 divided by 10. Now if you look at that, automatically that's sine 60. But now it becomes 2 times 60. So that's 16 times sine 120 degrees divided by 10. Now, the value of sine 120 degrees divided by 10 on computation, you have to be approximately 1.39 meter. Now, in contact, these values can be computed directly. Range, after having this value, you can do the same thing as the connection between them. The connection between the two of them is simple. You know that max is range max divided by 2. But the value here, the value of the range, you ask your question, why would this formula not work here? The reason is because this value here is not, this is maximum height reached, but this range here is not at maximum. It's not at maximum range. You still have theta is 60 degree. Theta can only be maximum when it is 45 degree. But at a point where the range is at maximum, then this formula becomes valid. But if both of them are at maximum, it's valid. But if it's not maximum, it is not valid. So it is valid when both of them are at maximum level. Now, we're going to consider the next aspect of projectile, which is the vertical projectile. Now, if for example I'm at a certain height and I decide to shoot a tennis ball or throw a stone from here, it will go with an initial velocity meter per second to go and hit the ground. It's still applicable to me having, this is the ground level, applicable to me having the same thing with, maybe this is a wall, and I throw a tennis ball, it hits this place, and when it hits this place, it bounces back. It's still the same thing. But it bounces back with an initial velocity, u meter per second. Good. Now, we're going to use this to do value explanations. This is the height of the body. Right from here to here is the range, and we know that range is ut. That's what we discussed initially. Range is equals to ut. Initial velocity times time, and this is the height of the body. Good. Now, this height of the body, at every instances that this body is moving, it creates a junction of this nature. Creates a junction of this nature. Where this is the vertical uy and this is ux, uy and this is ux. Now, we all remember that s is equals to ut plus or minus half gt squared. We know that. Now, if this body is coming down, surely the value of u as the body is coming down is equals to 0 from your knowledge of motion under gravity. As this body is coming down, the value of u is 0. So let me replace now. Let me say distance, which is a meter, is now represented as height. And let me say the time of flight of this expression is now capital letter T. So from this, and we know very well that the value of u is equals to 0. So from here I can place this out to become height is equals to 0 into bracket T. The gravity is under gravity. So because it's under gravity, it's going to become plus g t squared. So I will have height divided by 2. So I will have height is equals to g t squared over 2. If I cross multiply this statement, I will have 2h is equals to g t squared. So t squared now will give me 2h over g, and t will give me square root of 2h over g. So for this kind of tragedy, a vertical projection, take note of this, that the time of flight from here to here is 2h over g. 2 times the height divided by gravity, or square root. Now, but recall this, that range r is equals to ut. What is ut? Initial velocity times the time of flight. That now make range to become u times square root of 2h g. So therefore, you can boldly say that the range of the tragedy is u root of 2h over g. So, another important formula. So you have that. Now, the velocity of impact is the velocity of impact, or when it just hit the ground, is given as V is equals to GT. Just take note of this. So now I have three formulas. The first one is that time is equals to square root of 2h over g. The second is that the range of the tragedy is u square root of 2h over g. And the last, which is not the least, is that the velocity at which it hits the ground, immediately it's thrown, is coming down. The velocity at which it just hit the ground, at which it just impacted the ground, is equals to gt. Gravity times the time of light. Beautiful. So, from there, we are going to take a question on this before we take the tragedy analysis. Okay, the question on a vertical projectile, or the tragedy of a projectile. Now, a ball is thrown horizontally from the top of a cliff 20 meters high. The first thing you do is that you outline the values. Your height is 20 meters. 20 meters high. If the initial horizontal velocity is 8, the initial horizontal velocity, which is the initial velocity, u is equals to 8.0 meter per second. Good. Now the next thing is, find how long it takes to reach the horizontal plane at the foot of the cliff. How long does it take? The time it takes, which is the first question, is t, and it's equals to square root of 2h over g. That gives a value of square root of 2 times 20 divided by 8. And that gives a value of square root of 40 divided by 8. And that gives a value. If 2 goes here, you have, if 4 goes here, you have 10. And if 4 go here, you have 2. 2 here, 1, 2 here, that's 5. That gives square root of 5. So from your value, you have square root of 5, which is also equal to approximately 2.4 seconds. Good. From here, we have something of B, which is, it said how far from the foot of the cliff it strikes, how far from the foot of the cliff it strikes the ground. How far from the foot of the cliff it strikes the ground. It's simple. It's just as if you have something of this nature and you have this. So the foot of the cliff where it hits the ground is the range. How far from the feet down to where it hits the ground, from the feet where it hits the ground is the range. And what's the value of range? Range is ut. And what's the value of u? U is 8.0 then T is 2.24. And multiplying this, that should be 17.92 meter. Now, the last but not the least is the speed with which it strikes the ground. That is C. The speed with which it strikes the ground is V, and it's equals to GT. And what is the value of G? The value of G is 10. The value of T, what's the value of T, is 2.24. That will give us 22.4 meter per second. So you have this. The first, 2.24 seconds. The second, which is the range, 17.92 meter. And the last but not the least is 22.4 meter per second. Now, before we round it up on vertical projection, let's talk about the velocity, resultant velocity at every instance on the trajectory. At every instance on the trajectory. Now, that instances, if you look at the trajectory I gave to you, at every instances you have something like this. You observe that at every instance you have a right angle triangle like structure where here is U, Y, and you have UX. Now the resultant velocity is obtained from here, which is resultant velocity R. So that resultant velocity VR is equals to square root of UY squared plus UX squared. That's the resultant velocity. Please take note of that. Okay. So that that's an angle alpha. So that angle alpha is UY over UX. Okay, sorry, so that it becomes alpha is tan inverse of UY over UX. So you have these two kept by the side. So always remember the resultant velocity at every instances on the trajectory is 1. The resultant velocity is the initial velocity, the componental value of the initial velocity at vertical position and that at horizontal position, both on square. Then the angle between them, because it's a vector quantity and it must have, as it has magnitude, it must have direction. So the direction is tan inverse of U vertical component and horizontal component. We come to the end of this class for projectile. Thank you very much.